This section's title tells us we're dealing with a machine learning model called PassiveAggressiveClassifier and how to adjust its settings, called hyperparameters, to make it work better. It's like tuning a car engine, you tweak different parts to optimize its performance. This is the core question. We're given 4 different statements and have to figure out which ones are correct about improving the model's performance on new, unseen data. We need to understand the function of each hyperparameter to answer this. The _max_iter parameter controls the number of learning cycles. Think of it like repetitions in a workout. More iterations mean more learning, potentially a better model, but it also takes longer to train. The _loss equals hinge setting uses a loss function that pushes the model to create a wide gap between different data categories. This is similar to how support vector machines, SVMs, work. I think of it like creating a clear boundary between different groups of items. The _fit_intercept parameter simply adds a constant term to the model's equation. It does not magically handle complex curved relationships between the data. This is an important detail for our quiz. The _c parameter controls the model's complexity. Increasing _c actually increases complexity, potentially causing overfitting, where the model performs great on the training data but poorly on new data. ICC is a regularization parameter. A smaller c means stronger regularization, leading to a simpler model which might generalize better. A larger c allows for more complex models, but could lead to overfitting. Think of it like this. A smaller c is like a stricter teacher, keeping the model simple and focused, while a larger c is a more lenient teacher, allowing more room for complexity. Pretty cool, huh? This parameter determines whether to add an intercept term. The intercept shifts the model's prediction, allowing it to better fit the data. Think of the intercept as adjusting the starting point of a line. It's crucial for accuracy, but it doesn't magically handle nonlinear relationships. PassiveAggressiveClassifier is inherently linear. To handle nonlinearity, you'd need a different type of model. It's all about choosing the right tools for the job. The loss parameter defines the loss function. Hinge loss is similar to what support vector machines, SVMs, use. It encourages a wide margin between different classes. Imagine 2 groups of points. A hinge loss function tries to draw a line as far away from both groups as possible. This helps the classifier to be more confident in its predictions. It's all about maximizing the margin. This controls how many times the learning algorithm runs through the data. More iterations can lead to a better solution, but it also takes longer. Think of it as the number of practice sessions for a sports team. More practice improves skill, but takes more time. You need to find a balance between accuracy and training time. Finding that sweet spot is key, my friend. This is the type of model we're using. It's a linear model, meaning it creates linear decision boundaries to separate classes. The parameters we've been discussing are how we fine-tune its behavior. Remember that it doesn't inherently handle curves. I'm tuning a passive-aggressive classifier, a machine learning model. I'm focusing on its hyperparameters, the settings I can adjust to improve its performance. It's like tweaking the knobs and dials on a really powerful sound system to get the perfect mix. I'm answering multiple choice questions about how those settings affect the model. I need to understand how each setting impacts the model's ability to generalize well to new, unseen data. It's like testing different sound system settings to see which sounds best in different rooms. I'm training a text classifier using Python's scikit-learn library. My goal is to improve the model's ability to classify new text it hasn't seen before. We're examining statements to find the ones accurately reflecting the hyperparameter tuning process. It's like training a dog to recognize different commands. I want to make sure it performs well on new commands as well. Once I've tuned my hyperparameters, I'll evaluate how well my model performs on new data. This refinement process is an iterative loop. I'll adjust my hyperparameters based on these evaluations to create a model that accurately classifies new data. Think of it like baking a cake. You taste test the cake to see if you need more sugar or less flour and refine the recipe to get the best result. Let's dive into tuning the PassiveAggressiveClassifier. We'll explore how tweaking its settings impacts the model's performance. Think of it like adjusting the knobs on a sound system. You want the best audio quality, right? Similarly, we're aiming for the best model performance. We'll focus on these hyperparameters: C, fit_intercept, loss, and max_iter. Each one plays a unique role. I see you're curious about the loss equals hinge setting. This is super important because it dictates how the model learns. Think of it like this. Imagine you're drawing a line to separate two groups of data points. The hinge loss wants to create a wide gap, margin, between those groups. The wider the margin, the better the model's ability to generalize to new, unseen data. That's what support vector machines, SVMs, already aim for, and this setting brings that same philosophy into our classifier. Now, let's talk about max_iter. This controls how many times the model repeats, its learning process. More iterations might mean a more accurate model, but it will also take longer to train. It's a trade-off between precision and time. We want the model to settle on the best possible settings, but we don't want to wait forever, right? Think of it like baking a cake. You want it perfectly baked, but you don't want to keep it in the oven for hours and hours. This one deals with how the model accounts for the baseline offset in the data. Imagine fitting a line through points fit_intercept determines whether you can adjust that line's vertical position for the best fit. It doesn't, however, magically turn a linear model into one that handles curves. It's a crucial piece for accurate linear modeling, but not for nonlinear data issues. Let's clear up any confusion around the C parameter. C is about regularization. How much we penalize the model for complexity. A larger C actually allows for a more complex model, increasing the risk of overfitting, memorizing the training data instead of learning general patterns. Smaller C values lead to simpler models. Think of it like this. A large C is like giving your model free rein to get as complex as it wants, but that might not be great for handling new data. I see that C controls the strength of regularization in the passive-aggressive classifier. A smaller C means stronger regularization. This simplifies the model, which can prevent overfitting and improve performance on new, unseen data. A larger C weakens regularization, allowing a more complex model that might overfit the training data. Think of it like this. A smaller C is like putting a leash on a dog, your model, to prevent it from getting too wild, overfitting, and a larger C is like letting the dog run free, maybe getting the job done quicker, but also likely to make mistakes. The max_iter parameter determines how many times the passive-aggressive classifier's training algorithm iterates through the training data to find the best model. More iterations can lead to better model accuracy as the model has more opportunities to learn from the data. However, more iterations also mean longer training times. You have to find the sweet spot balancing accuracy and training speed. This part is all about how you train and test the passive-aggressive classifier. You'll need training data to teach the model and validation, or test, data to see how well the model generalizes to new, unseen data. Performance metrics, like accuracy, help you evaluate how well your model is doing. This is crucial for avoiding overfitting. The fit_intercept parameter simply determines whether to add a constant term, an intercept, to your model. Think of it as adjusting the baseline prediction. It doesn't deal with nonlinear relationships directly. Passive-aggressive classifier is inherently linear. The loss equals hinge setting uses a hinge loss function. What does that mean? It means the model aims to create a large margin, a wide gap, between different data categories, making classifications more confident and less prone to errors. It's similar to how support vector machines, SVMs, work, focusing on clear separation. The max_iter parameter dictates the number of times the model iterates through the training data during training. More iterations can improve the model's convergence. It gets closer to an optimal solution, but increases training time. Finding the right balance is key. This question tests your understanding of how different hyperparameters in the passive-aggressive classifier affect the model's behavior, particularly its ability to generalize to new data. This is the overarching topic, focusing on how to adjust the settings, hyperparameters, of a passive-aggressive classifier to optimize its performance. The "loss" function defines what the passive-aggressive classifier is trying to minimize during training. The "hinge" loss is particularly well suited for classification tasks because it encourages the model to produce classifications with a wide margin of confidence. I'll explain the hyperparameters we use to fine-tune a passive-aggressive classifier model. Think of these as knobs and dials you adjust to optimize the model's performance. We'll focus on 4 key hyperparameters: "C", "fit_intercept", "loss", and "max_iter". The "max_iter" hyperparameter controls how many times the algorithm iterates through the training data to learn. More iterations, generally, lead to a better fit to your training data, but it also takes longer. It's a trade-off between accuracy and computation time. I'd experiment to find the sweet spot. The "loss" hyperparameter dictates how the algorithm measures errors during training. "loss" equals hinge means it uses the hinge loss function, which aims to maximize the margin, the distance, between different data classes. This is a key feature of support vector machines, making the passive-aggressive classifier behave in a similar way. The "fit_intercept" parameter determines whether to add a constant term, an intercept, to the model's equation. While it affects the model's overall accuracy, it doesn't directly handle nonlinear relationships. Think of it this way: it shifts the decision boundary, but it doesn't change the boundary's shape. A passive-aggressive classifier is a linear model. You'll need other techniques for nonlinear data. The "C" hyperparameter is a regularization parameter. Smaller values of "C" encourage simpler models, which are less prone to overfitting, performing well on training data but poorly on unseen data. Conversely, larger "C" values allow for more complex models, which might overfit. The statement incorrectly says increasing C simplifies the model. The opposite is true. This is the overall topic of our discussion. We're trying to understand how to tune the various settings, hyperparameters, of a passive-aggressive classifier to get the best performance from our model. I'll break down each hyperparameter for you individually. Once you've tuned your hyperparameters, you'll train your passive-aggressive classifier using your training data. After training, you need to evaluate the model's performance. This generally involves splitting your data into training and testing sets and checking how well the model generalizes, performs, on unseen testing data. We're tuning the hyperparameters of the passive-aggressive classifier, a machine learning model used for text classification. Think of hyperparameters as the knobs and dials we adjust to optimize the model's performance. We want to find the settings that make the model generalize well to new, unseen data, making accurate predictions on data it hasn't seen during training. This is crucial for building a reliable model. I disagree with this statement. The C parameter controls regularization strength. A smaller C means stronger regularization, leading to a simpler model. Increasing C weakens regularization, making the model more complex and prone to overfitting. It learns the training data too well and performs poorly on new data. It's like trying to memorize an entire textbook versus understanding the key concepts. This statement is false. The "fit_intercept" parameter simply determines whether to add a constant term, the y-intercept, to the model's equation. It doesn't change the model's ability to handle nonlinear data. The passive-aggressive classifier itself is a linear model. To deal with nonlinearity, you'd need a different model altogether. That's correct. This is true. The hinge loss function tries to maximize the margin, the gap, between different classes in the data. This is a key feature of support vector machines, SVMs, and using "loss equals hinge" makes the passive-aggressive classifier behave similarly. Absolutely correct. This is also true. "max_iter" controls the number of iterations the model goes through during training. More iterations can lead to better convergence. The model gets closer to the optimal solution, but it also takes longer to train. It's a trade-off between accuracy and training time. This is a multiple-choice question testing your understanding of passive-aggressive classifier hyperparameters and their effects on model performance and generalization. You have to select the correct statements about how these settings affect the model's behavior. It's all about choosing the right settings to get the best results.